Here's what I want you to do. Right now, in your seat, I want you to notice that time is passing. Go ahead, feel it. That sensation you have, the sense that this moment is sliding into the next one, that the past is fixed and the future is open, that there is a river called now and you are being carried down it whether you like it or not. I want you to hold on to that feeling for one more minute, because in about 20 minutes, I am going to take it apart in front of you, piece by piece, using nothing but results that have actually been measured in actual laboratories, and I am not going to hand it back to you the same shape it came in. I'm not exaggerating for effect. I don't do that. I've spent 3 decades in rooms full of tensors and Hamiltonians, and I have learned exactly one lesson that matters more than any other. Your intuition about time is almost certainly wrong, and the universe does not care that it's wrong, and in the last decade we built machines that proved it. Let me tell you what actually happened, because the headline version, "Physicists create matter that breaks time," is the kind of sentence that gets clipped onto a thumbnail and stripped of everything that makes it true. I want to give you the real thing, not the cartoon. The real thing is stranger than the cartoon anyway, so you're not losing anything by insisting on it. Start here. What do you think time is? Don't answer out loud, just notice your gut reaction. Most of you are picturing something like a film strip, a sequence of frames, each one following the last, ticking forward at a steady rate, the same for everyone, everywhere. That's Newton's time. Absolute, universal, indifferent. A clock ticking in the sky that every clock on Earth is secretly slaved to. It's a beautiful picture. It's also been dead for over a century, and most people haven't been told. Einstein killed it in 1905, and I mean killed it, not refined it, not added some nuance, killed it. There is no universal now. Two events that are simultaneous for you can be in a different order for somebody moving relative to you, and neither of you is wrong. Time is not a river. Everyone floats down together. Time is a personal, local, geometric quantity, woven into the fabric of space itself. And it bends and stretches depending on how fast you're moving and how deep you are in a gravity well. You've heard this before, probably. GPS satellites have to correct for it, or your Uber driver ends up in the wrong county. Fine. Most people nod along at this point and think, okay, time is relative, got it, moving on. That is where almost every popular explanation stops, and that is exactly where I refuse to stop, because relativity, as strange as it is, still leaves something completely intact. It leaves the flow. Even in Einstein's universe, each observer still experiences time ticking forward, one moment after another, smooth and continuous. Relativity bent the ruler. It didn't touch the fact that the ruler has a direction and moves along it steadily. That's the assumption I'm here to demolish tonight. Not is time absolute. We buried that assumption 100 years ago and it isn't coming back. The assumption I'm going after is deeper. Is time even continuous? Is it smooth? Does it, at the most fundamental level matter can express, always look the same from one instant to the next? Or can matter itself develop a texture in time, a texture the way a crystal has texture in space? Now, here is where it gets strange. Think about an ordinary crystal. Salt, quartz, diamond. What makes it a crystal? Physically? Mathematically? The universe, left alone, prefers uniformity. A gas of atoms doesn't care where you put your coordinate origin. It looks statistically the same everywhere you measure it. That's called continuous translational symmetry, and it's one of the deepest ideas in physics. The laws don't play favorites with locations. But cool that gas down, let the atoms find their lowest energy configuration, and something remarkable happens. The atoms lock into a lattice. Suddenly, there are favorite locations, the lattice points, and everywhere else is disfavored. The symmetry that said every point in space is equivalent has been spontaneously broken down to a much smaller symmetry that says only these specific, evenly spaced points are equivalent. That breaking is not imposed from outside. Nobody reached in and forced the atoms into a grid. The grid emerged because it was energetically preferred. This is called spontaneous symmetry breaking, and it is one of the load-bearing walls of modern physics. It's how the Higgs field gives particles mass, it's how magnets get their north and south poles, it's how the early universe cooled into the four separate forces we experience today. Continuous symmetry, spontaneously broken down to discrete symmetry. Hold on to that phrase. You'll need it in a minute. Now, and this is the move that theoretical physicist Frank Wilczek made in 2012. And I remember exactly where I was when I first read the preprint, because I thought it was a joke. What if the same trick works on time? What if you could cool a system down, let it find its natural resting state, and have it spontaneously break time translation symmetry the same way a crystal breaks spatial translation symmetry? What if the system's lowest energy state wasn't static, wasn't just sitting there, but instead oscillated, all on its own, with no external clock driving it, no energy being pumped in, no motor, nothing? A perpetual, self-sustaining tick built into the very ground state of a quantum system. For free? Forever? That's a time crystal. And when Wilczek proposed it, half of theoretical physics got extremely excited, and the other half, correctly, as it turned out, said, wait a minute, that violates something sacred. Here's the problem, and I want to walk you through it because the failure is as instructive as the success. If a system in its true ground state, its state of absolute lowest energy, the state it settles into after all the excess energy has drained away, is oscillating, changing from moment to moment, then you've got a machine doing something for free, forever, with no energy cost. That smells exactly like a perpetual motion machine. And perpetual motion machines are not just difficult, they are forbidden. They are the one thing in physics that is never, ever allowed, because they would violate the most battle-tested law we have, the conservation of energy dressed up in its statistical mechanics clothes. A mathematical physicist named Haruki Watanabe, working with Masaki Oshikawa, proved a rigorous no-go theorem in 2015. In true thermal equilibrium, in the actual ground state, spontaneous time crystalline order is impossible, full stop. The idea, as originally stated, was dead on arrival, killed by the very framework that gave birth to it. I want you to sit with that for a second, because this is the part people skip. Wilczek's beautiful idea got shot down by rigorous mathematics within 3 years. That's not failure, that's physics working exactly as designed. Half the job of a good idea is dying quickly and cleanly so that the good part of it can be salvaged and the bad part can be buried. And here's what got salvaged. The no-go theorem only killed the equilibrium version. It said nothing, nothing at all, about systems that are being periodically kicked, driven, pushed from outside, systems that never settle into a boring ground state because you keep shoving energy through them in a rhythm. Those systems live in what's called a Floquet phase, named after the 19th century mathematician who studied periodically varying differential equations. And Floquet systems don't obey the same rules as equilibrium systems because they are never, technically, at rest. So the question changed shape. Not, can a system tick on its own in true equilibrium? No, that's forbidden. But if I drive a system with a period t, can it respond with a period 2t, or 3t, or some multiple that has nothing obviously to do with my driving frequency? And can it do that stably, robustly, resisting noise and imperfection the way a crystal resists having its atoms nudged slightly out of place? That's the real definition of a discrete time crystal. And notice what it requires. It requires the system's response to not match the rhythm you're forcing on it. You push it once every second, and instead of it doing one thing every second like a sane, boring, driven system would, it does one thing every 2 seconds. It's subdividing your beat into its own beat. It's breaking the discrete time translation symmetry of your periodic drive down to an even smaller, more sparse symmetry. Exactly the same mathematical move a spatial crystal makes with a continuum, except now it's happening in time. This is not obviously possible either, by the way. Driven systems normally heat up. You keep shoving energy in, the system absorbs it, gets hotter and hotter, and eventually turns into a structureless thermal soup that has forgotten everything about its own internal order, the same way a chunk of ice, banged on repeatedly, eventually just melts into an undifferentiated puddle. For a genuine, discrete time crystal to survive, you need the system to resist that heat death long enough for the ordered, period-doubled behavior to actually be measured and to actually be robust against the messiness of a real laboratory. Theorists worked out that a particular kind of disorder-induced localization, many-body localization, if you want the term, could act like a refrigerator, keeping the system from thermalizing, letting the period-doubled order survive far longer than it has any right to. This stopped being a napkin argument in 2016 and 2017. A group led by Christopher Monroe, using a chain of trapped ytterbium ions held in an electromagnetic trap and hit with laser pulses in a careful periodic sequence, watched the ions' collective magnetization flip in a pattern that repeated every 2 drive cycles instead of every 1, and it stayed locked to that period-doubled rhythm even when they deliberately messed with the driving frequency, which is exactly the signature you'd demand before you believed it. Around the same time, a Harvard group led by Mikhail Lukin did something structurally similar using nitrogen vacancy centers in diamond, trillions of them, not a handful of ions, a genuinely macroscopic, room-temperature, solid-state system, and saw the same period-doubled, drive frequency-defying ticking. 2 completely different physical platforms, 2 completely different experimental teams, converging on the same impossible-sounding behavior within months of each other. That's when I stopped thinking of this as a cute theoretical curiosity and started rearranging my lecture notes. And then in 2021, a team working with Google's Sycamore superconducting quantum processor, the same lineage of machine that had made headlines a couple years earlier for so-called quantum supremacy, used dozens of programmable superconducting qubits to realize what they called a prethermal discrete time crystal, published in Nature. And this is the one I actually want you to picture, because it's the cleanest demonstration I know of. They set up a chain of qubits, drove them with a repeating pulse sequence, and measured how the qubits' collective state evolved cycle after cycle after cycle. A normal-driven system, if you plotted its state against time, would show you a signal oscillating at the drive frequency, boring, expected, matching your input like an obedient student. What they saw instead was a signal that oscillated at exactly half that frequency, locked there, stable there, for far longer than any naive estimate would allow, robust against exactly the kind of imperfections that should have washed it out in an instant. The qubits, collectively, had found a rhythm of their own that subdivided the experimenter's rhythm, not because anyone told them to, but because it was the energetically, dynamically preferred thing for the many-body system to do, the same unforced, emergent preference that turns a disordered gas into a perfectly ordered lattice. Let me give you the concrete picture, because I promised you tactile and I meant it. Imagine a metronome, ticking once per second, completely regular, completely boring. Now imagine dozens of tiny quantum spins, each one influencing its neighbors, and imagine that instead of letting them settle quietly, you hit the whole array with a pulse every time the metronome ticks. A dumb, obedient system would flip once per metronome tick, and you'd measure a signal at exactly 1 cycle per second, matching your metronome perfectly, the way a soldier matches a drill sergeant's cadence. That's what almost every physical system in the history of physics does when you drive it periodically. What the Google team actually measured, cycle after cycle, was a signal that flipped once every 2 ticks, half the metronome's rate. And it kept doing that even when they deliberately fumbled the metronome's timing, sped it up a little, slowed it down a little, roughened the pulses. The 2-tick rhythm didn't care. It held. That stubbornness, that refusal to follow the beat you're setting in favor of a beat it invented for itself and then defended against your interference, is the signature that convinced skeptical referees to publish it. And it's the same stubbornness a real crystal shows when you push on it and it resists deforming, snapping back into its lattice instead of smearing into a formless blob. Rigidity, but in time instead of space. That's the whole idea, held in your hand. Now let me tell you why this is not just a neat trick, because you deserve the why, not just the wow. For the entire history of physics, up until about a decade ago, we organized matter by symmetries broken in space. Solid, liquid, gas, magnet, superconductor, every single phase of matter you've ever heard of is defined by which spatial symmetry it breaks and how. Time crystals are the first new type of order human beings have ever discovered that lives natively in the time dimension instead. We had, for the entire span of scientific history, one half of a classification scheme. We just found the other half. That's not an incremental result. That's opening a drawer physicists didn't know was there, in a filing cabinet we thought we'd fully cataloged a century ago. But, and here's where I have to be the guy in the room who won't let you walk away with the wrong idea, I need to correct something, because this is exactly the kind of result that gets mangled on the way to a headline, and I will not stand up here and let that happen in front of me. A discrete time crystal does not mean time itself is crystallized, frozen, granular, made of little indivisible chunks like sand. It does not mean the universe has a fundamental tick rate. It does not mean we've discovered that time is secretly discrete the way some quantum gravity theories speculate space might be at the Planck scale. What we've shown is that matter, driven periodically, can spontaneously organize its behavior into a rhythm that subdivides the imposed rhythm, an emergent property of many interacting particles, not a fact about the underlying continuum of time itself. If you go home and tell your friends, physicists proved time is made of pixels, you are going to embarrass both of us. And I say that with love, but I say it directly, because that's exactly the kind of half-truth that spreads faster than the real one, and I'd rather you not be a vector for it. What it does mean, and this is the disturbing part, the part I actually promised you, is this. The smoothness we assume time has, the sense that now flows continuously and uniformly into next, is not some untouchable, sacred, unbreakable feature of physical law. It's a symmetry. And symmetries, we have learned again and again across 100 years of physics, are things that break under the right conditions. We already knew space's uniformity could break. That's every crystal on Earth. That's the salt on your table. We now know time's uniformity can break too, under the right-driven, many-body conditions. The floor you thought was solid, smooth, continuous, monotonic time has a trapdoor in it, and we found where it is, and we walked a system through it in laboratories in Maryland and Massachusetts and Santa Barbara. I made a mistake early in my thinking about this that I still think about more than I'd like to admit, and I'll tell you about it because pretending I always saw this clearly would be a lie, and I don't do those from a podium. When many-body localization first started circulating as the mechanism that might let discrete time crystals survive against thermalization, I assumed, wrongly, and said so out loud in a seminar I still wince about, that any periodically driven system would inevitably heat to what's called infinite temperature, a featureless thermal soup with no memory of its own structure, given enough time, and that the disorder-protected version was a curiosity that would only ever survive in idealized, one-dimensional toy models, never in a real, warm, noisy laboratory with dozens of qubits and imperfect control pulses. I was wrong in a specific and instructive way. I underestimated how robust a pre-thermal phase can be, a phase that isn't eternally stable in the strict mathematical sense, but that survives for a stretch of time so astronomically long compared to any timescale you could practically measure that the distinction stops mattering for the purposes of an actual experiment. The Google collaboration didn't need eternal time crystalline order. They needed order that outlasted their experiment by orders of magnitude, and pre-thermalization delivered exactly that. I don't enjoy telling that story, but you should always be suspicious of a physicist who never admits getting a prediction wrong. I told you at the start I'd take apart your sense of time's flow. I'm not finished. There's a second front in this argument, and it's older, and honestly, it unsettles me more than the time crystal does, and I want you to understand why. Every fundamental equation of physics you can write down, Newton's laws, Maxwell's equations, the Schrödinger equation, Einstein's field equations, every single one of them is time-symmetric. Run the equation forward, run it backward, both are equally valid solutions. If I filmed two billiard balls colliding and showed you the film forward and then backward, you could not tell, from the physics alone, which direction was the real one. The fundamental laws simply do not know which way time is supposed to go. And yet you have never in your life seen a shattered wine glass leap up off the floor and reassemble itself in your hand. You have never seen smoke pour itself back down a chimney into a fire. Every single one of you experiences time as having an unmistakable, undeniable arrow. The future is where entropy increases, the past is where things were more ordered, and not one fundamental equation of physics puts that arrow there. It comes from somewhere else entirely. From the statistical fact that there are vastly, overwhelmingly more disordered configurations of matter than ordered ones. So overwhelmingly more that a system left alone will, essentially by sheer weight of probability, wander from an ordered state toward a disordered one and essentially never wander back. Not because it's forbidden, but because it's like shuffling a sorted deck of cards. It's not impossible to reshuffle your way back to sorted. It's just so staggeringly unlikely that you will not see it happen in the lifetime of the universe. This is not a new observation, and I want to give credit where it's owed, because the argument is over a century old and it's one of the sharpest in the history of physics. In 1876, Joseph Loschmidt confronted Ludwig Boltzmann with what's now called Loschmidt's paradox. Your dynamical equations are time-symmetric, Boltzmann, so how dare you derive an asymmetric conclusion, entropy relentlessly increasing, the famous H theorem, from perfectly symmetric machinery? It's a real paradox, not a dumb objection, and Boltzmann's answer, when you strip away a century of textbook polish, essentially comes down to this. The arrow isn't hiding in the dynamics, it's hiding in the initial condition. The universe, or at least the corner of it we live in, started in an extraordinarily low entropy state, and everything we call the flow of time, memory, causation, the difference between the past you remember and the future you don't, is really just entropy climbing away from that one special, ridiculously unlikely starting point. Which means the arrow of time isn't a law of physics at all. It's a fact about history, about one boundary condition fixed near the Big Bang that we have never adequately explained from first principles. Why was it low entropy then? Why is there an arrow at all? We genuinely do not have a settled answer, and anyone who tells you we do is selling you something. I've sat in rooms with very serious cosmologists who disagree sharply on this, and I'll be honest with you, some nights it's the question that keeps me up more than anything else in this entire subject, because it means the most basic feature of your lived experience, the fact that yesterday is fixed and tomorrow is open, is not written into the fundamental laws of the universe at all. It's an accident of where we happen to be standing in cosmic history. And there's a third front, and I'll be careful about this one because it's the strangest and I don't want to overstate it. When physicists try to write down a quantum theory of gravity, to marry Einstein's smooth, dynamical spacetime to the discrete, probabilistic rules of quantum mechanics, one of the central equations that keeps showing up, the Wheeler-DeWitt equation, describing the quantum state of the universe as a whole, has no time variable in it. None. It's a single, static equation. Time simply does not appear as an ingredient. Physicists call this the problem of time in quantum gravity, and it has been open, genuinely open, unresolved, since the 1960s. Some serious researchers, Carlo Rovelli's thermal time hypothesis is the one I find most compelling on a good day and least compelling on a bad one, argue that time isn't fundamental at all, that it emerges the way temperature emerges from the statistics of countless jiggling molecules, that there is no time at the bottom of reality, only relationships between physical quantities and what we call time is a bookkeeping device that appears once you're a large, thermodynamic, entropy-generating observer embedded inside the system rather than looking at it from outside. I am not telling you that's settled. It is not settled. Plenty of extremely competent people think it's a beautiful answer to the wrong question. I genuinely do not know who's right, and I have opinions I won't bore you with tonight, and none of them are certainties. There's a fourth front, and I want to give it to you carefully, because it's the one most likely to get exaggerated into nonsense by the time it reaches a headline, and I would rather correct it myself than let you pick up the wrong version somewhere else. You've probably heard some version of the claim that quantum experiments have shown effects happening before their causes, that physicists have proven the future can reach backward and change the past? That claim, stated that baldly, is false. And I want to be blunt about it, because it does real damage to public understanding of a genuinely strange result by replacing it with a cheap, wrong one. What's actually true is stranger than the myth, not tamer than it, and I want you to have the real version. In the early 2010s, a theorist named Czaslaw Bruckner and collaborators started asking a very specific question. Does quantum mechanics require that events happen in a definite causal order at all? A causes B, full stop, one direction? Or can a quantum system be placed in a superposition of causal orders themselves? Not a superposition of outcomes, which you already know about from ordinary quantum mechanics, where a particle can be in a superposition of here and there, a superposition of the order in which two operations happen, a genuine quantum, which happened first, that isn't settled until you measure it. They called the theoretical device a quantum switch, and for years it lived entirely on paper, a mathematically consistent but experimentally untested idea. Then, starting around 2015, several groups, a team led by Philip Walther in Vienna, and separately groups in Brisbane and in China, built actual optical circuits using photons and beam splitters that realized this quantum switch in the laboratory. Here's the structure, stripped down. You send a single photon toward two devices, call them Operation A and Operation B, that each do something small to the photon's state. In the ordinary world, you'd have to pick an order, A, then B, or B, then A, and the two choices generally give you different final results. The way putting on your socks, then your shoes, gives a different outcome than putting on your shoes, then your socks. What these experiments did was route the photon, using its own quantum superposition, through a circuit where it takes both orders at once, coherently, in superposition, genuinely indefinite about whether A happened before B or B happened before A, in exactly the same formal sense that an electron in a double-slit experiment is genuinely indefinite about which slit it went through, right up until you measure it. And they showed, experimentally, that this indefinite order configuration produces statistical outcomes, correlations you can actually measure with photon detectors, that cannot be reproduced by any experiment where the causal order is fixed in advance, even a hidden, unknown-to-you fixed order. That's the rigorous part. It's not a philosophical flourish. It's a Bell-type inequality violation, the same style of airtight statistical argument that ruled out local hidden variables in the 1970s and 80s, now ruling out definite causal order. Notice, and I want to be precise here because this is exactly where the myth creeps in, that nothing in this experiment sends information backward through time. Nothing here lets a future measurement influence a past event in a way you could exploit to send a signal to your own past self, which would blow a hole clean through causality and, frankly, through most of what makes physics a coherent discipline at all. What's being shown is something subtler and in some ways more radical. That the very notion of which event came first, something we treat as the most basic, non-negotiable scaffolding underneath physics, more basic even than space, more basic than energy, is, at the quantum level, not always a well-defined fact about the world. It's a variable, like position or spin, that can be genuinely undetermined until measured. We built causal order out of Newton's absolute time and never fully let go of it, even after relativity relativized simultaneity. Because relativity, remember, still guarantees a definite causal structure for any two events connected by a signal traveling slower than light. Event A causes event B, and every observer, however they're moving, agrees on that ordering. The quantum switch experiments show that this guarantee, this bedrock assumption that causal order is always a settled fact, breaks down in exactly the regime where quantum mechanics and the geometry of space-time have to be reconciled, which is precisely the regime theorists trying to build a quantum theory of gravity are staring into. Because at the smallest scales, where space-time itself might be quantum, the very idea of before and after between two locations might not survive intact. I bring this up not to pile on shock value, but because it connects directly to the argument I'm building. We started with relativity dissolving a universal now. We moved to time crystals dissolving the assumed smoothness of time. We went to entropy dissolving the fundamentality of the arrow. And now the quantum switch experiments dissolve something even more basic. The assumption that this happened before that is always, in every circumstance, a fact of the matter. 4 separate experimental programs, 4 separate decades, 4 separate techniques, atomic clocks on airplanes, trapped ions and superconducting qubits, statistical mechanics and cosmology, photons and beam splitters, and every single one of them chips away at a different plank of the same wooden floor you've been standing on your entire life without ever once looking down. So let's put the pieces on the table together, because that's the actual disturbing part, not any one piece alone. 1. Relativity already told us there's no universal, shared now. Time is local, geometric, bendable. 2. The time crystal experiments tell us that even the texture of time, its assumed smoothness, its assumed uniformity from moment to moment, is a symmetry that matter can spontaneously break, the same way it breaks spatial symmetry into a crystal lattice. 3. The arrow of time, the very thing that makes tomorrow feel different from yesterday, isn't in the fundamental dynamical laws at all. It's a statistical accident hitched to a boundary condition at the birth of the universe that we cannot yet explain. And underneath all three, in the deepest equations we have for gravity and quantum mechanics together, time might not be a fundamental ingredient of reality at all. It might be something that emerges, the way wetness emerges from water molecules that are not, individually, wet. You walked in here with a picture of time as a river, universal, smooth, one-directional, fundamental. I have taken every single piece of that picture apart in front of you with results that came out of real laboratories and real, peer-reviewed mathematics. Not speculation, not a thought experiment I made up to sound clever. It is not universal. Einstein, 1905. It is not necessarily smooth, the time crystal experiments, 2016 through 2021. Its one-directionality is not a law, but an accident of cosmic history whose origin we do not understand, Boltzmann and Loschmidt, still unresolved 150 years later. And it may not even be fundamental, the problem of time and quantum gravity, still open 60 years later. Here's what I actually believe, for what it's worth, and I'll tell you straight because you sat through the argument and you've earned the payoff. I don't think we've discovered that time is an illusion. And I get genuinely annoyed at people who use these results to say, time isn't real, man, as if that's a profound conclusion instead of a lazy one. Your subjective experience of time passing is completely real. It's just not what you thought it was. It's not a fundamental river you're floating on. It's closer to something a system like you, a hot, complicated, entropy-generating, memory-storing arrangement of matter, necessarily constructs from the inside. The way a wave is a completely real pattern in the ocean, even though there's no wave stuff separate from the water that composes it. The disturbing part isn't that time is fake. The disturbing part is that something so basic to your entire existence, the fact that you remember the past and not the future, the fact that this sentence is ending and not beginning, is not a law handed down from the foundations of physics. It's an emergent, statistical, historically contingent fact that we can now break in a laboratory with lasers and superconducting qubits, and that we still, after 150 years of trying, cannot fully explain the origin of. I'll leave you with the question that actually matters, the one I don't have an answer to, the one that will still be open when everyone in this room is gone. If the arrow of time comes from a low-entropy boundary condition we can't yet explain, and if the very continuity of time can be spontaneously broken by ordinary matter under the right periodic driving, and if time itself might not appear at all in the deepest equations we can write for the universe as a whole, then the question is not, what is the nature of time? The question is, what exactly are you, a thing that experiences a flow which may not be fundamental, remembers a direction which may be nothing but an accident of where the dice happened to land nearly 14 billion years ago, and calls all of that, with total and unshakable confidence, now? Go argue about that one on the drive home. I guarantee you won't finish before you get there.